We spent yesterday taking parent functions, linear, absolute value, quadratic, square root, and cubic, and shifting them left and right and up and down. Remember that if something is inside the parentheses or inside the absolute values or the square root or whatever it happens to be for that function, then it's moving it left or right. Adding moves to the left, subtracting moves to the right. That always seems to be a little bit backwards from what we think, since the positive values seem to be on the right instead of the left. So that one's going to seem backwards. If it's outside the parentheses or outside the absolute value or what have you, it moves the function up and down. And so we talked about those for each of those 5 parent functions. Today what we're going to do is talk about what happens when you multiply the slope or the rate. In a lot of the examples that we talked about, that's the a value. So for example, if we had the function y equals, let's pick something greater than 1, so 2x, our function gets steeper. The 0, 0 point still stays where it was. But the next one, if I plug in 1 for x, 1 times 2 is 2, and that's going to put my second point right here. So my graph is much steeper than it was for the original. So if I compare these two, this was flatter than the one I just came up with. We call that a vertical stretch. And that happens when I multiply something by a number greater than 1. If we multiply by a number less than 1, for example, if I say y equals 1/4 x, again, if I plug in 0, I still get out 0. 1/4 of 0 is still 0. But we know that with a slope of 1/4, we would rise 1 and run 4. And so this one is much flatter than our original. So we call that a vertical compression. And this will happen with each type of graph. So if we multiply by something greater than 1, it's a vertical stretch. By something less than 1, it's a vertical compression. So let's take another look here. Flip over to page 2 and look at the absolute value graphs. Let's say, for example, that I have the function y equals 3 times the absolute value of x. In this case, it's important for me to remember that when I plug in 0, absolute value of 0 is 0, times 3 is still 0, so I've still got my origin point at 0, 0, for my vertex. Then if I plug in 1 here, 1, the absolute value of 1 is 1, times 3 gives me 3, which puts my point right here. And then just like before, we're going to be symmetrical, so there's going to be 1 over here. Absolute value of -1 is 1, times 3 is 3. And again, we still have the V shape, but it is much skinnier and stretched. So again, this is a vertical stretch because I multiplied by something larger than 1. So the reverse is also true. If I say y equals 1/2 times the absolute value of x, I still have my point at 0, 0. But now if I were to plug in 2, I'm going to pick 2 because it's easy to work with. Absolute value of 2 is 2, half of 2 is 1. So it goes out 2 and up 1. Instead of out 1, up 1, it's going to take it much flatter. And again, we're symmetrical. And so again, I've got this graph that looks like it's been pushed down. That's a vertical compression. So again, flip to page 3. We're talking about a quadratic function, and these same rules apply. If I have y equals, let's say, 3x squared, I'm still going to have my origin point here at 0, 0. But if I plug in 1, 1 squared is 1, times 3 is 3. So all of a sudden, my graph is stretched pretty significantly to be much taller and skinnier, it seems. It's a vertical stretch. Or I could do something like y equals 1/2 of x squared. 0, 0 will stay where it is. But now if I plug in 1, I only get to go up a half. So 1/2 here and 1/2 here. If I plug in 2, for example, 2 squared is 4. Half of 4 is 2, would put the next point here and here. And so I'm just plugging in points to kind of help me with the shape. But this is a vertical compression. This is wider than this one. So we apply that same idea to square roots. If y equals 2 times the square root of x, my first point is going to stay at 0, 0, but the square root of 1 is 1, times 2 puts me here. So for every one we go out, we go up 2. So before we went out 4 and up 2, so now I'm going to go out 4 and up 4. Here. Or I could do y equals 1/2 the square root of x. They'll start at 0, 0. If I plug in 1, I only get to go by half this time. If I plug in 4, I get the square root of 4 is 2, and half of 2 is 1, which puts me right here. And so this grows much more slowly than the 1 next to it. The final example here is the cubic function. If I said y equals, let's say, 3x to the third power, my 0, 0 point won't move. If I plug in 1, 1 to the third power is 1 times 3 is 3, so that goes here. And if I plug in a negative 1, I get negative 3. And so I've got this graph that still looks like a cubic function, but is significantly stretched. And the last one here is, let's do 1/2 of x to the third. So I keep my 0, 0. If I plug in 1, 1 times 1 is 1, times 1 again is 1, and half of that would put me here. And negative 1 would be here. And so this is going to grow much more slowly than the last one did. There'll be a second video for this topic to talk about what happens when your a value is negative.